Good morning, students. In this lecture, we will study about systems characterized by linear constant coefficient differential equation. That means the input x of t is related to the output y of t by the differential equation. We studied this in chapter 2, if you remember. The differential equation relating the input and the output is given by from k is equal to 0, ak, the k's derivative of y of t by dtk is equal to, from k is equal to 0 to n bk, the derivative of the k's derivative of x of t by dtk, where n is the order of the differential equation. So if you remember, we were trying to find the output yt, which is the sum of the homogeneous solution and the particular solution, and it was tedious to find the output. But here we will use how Laplace transform can be used to find the output, the transfer function, which is h of s, y of s over x of s, and also given, for example, one of the variables given x of t, how we find x of t and yt, how we find h of t, and given h of t and x of t, how we find yt, and so on. So we will do the calculation in Laplace domain, and we change from Laplace domain to time domain. So we have here this system h of t, and the input is x of t and the output yt, and this is the differential equation that we said earlier. Now, from the derivative property, the derivative of x of t is s times x of s, and that means the k's derivative of x of t by dtk will be s power of k times x of s. And from the relation between y of t and x of t, y of t is equal to x of t convolved with h of t. This is from convolution. And from convolution property, the Laplace transform of this is y of s is equal to x of s times h of s. Then h of s is equal to y of s over x of s, which is called the transfer function of the system. We call this the transfer function. When this is evaluated at s is equal to j omega, we have h j omega is equal to y j omega over x j omega, which is the frequency response of the system. This one, we studied it in the chapter 3. What is y of s over x of s? Now we have this, the left side, we change it to Laplace domain. What is the k's derivative of y of t by dtk? It will be s power of k times y of s. And what is the k's derivative of x of t by dtk? It will be s power of k times x of s. So we have also the summation on the left side, and we have the summation on the right side. If we rearrange this, y of s over x of s will be summation from k0 until m bk s power of k over summation from k0 until n ak s power of k. This is compact form. If we expand this, it will be when k0, it will be b0, when k1, b1 times s, when k2, b2 s squared, and so on. Finally, bm s power of m over, when k0, the denominator a0, and when k1, a1s, when k2, a2s squared, plus plus plus, and when k capital N, an s power of n. This is equal to h of s, and we call this the transfer function of the system. And h of s is n of s over d of s, where n of s is the numerator polynomial, which is, it's a function of s, it's a polynomial function, as you see, function of s, and d of s is the denominator polynomial. So when we solve d of s is equal to 0, we will get the poles of h of s, the poles of the transfer function. And when we solve n of s is equal to 0, we will get the zeros of the transfer function. So by looking the region of convergence of h of s, we can talk about the system also, whether it is stable, whether it is causal, whether it is unstable, and anti-causal, and so on. Now let's see this simple example. This RC circuit. We did this example before for the frequency response. Now let's try to find the transfer function using Laplace transform. This is a simple RC circuit. The input voltage is Vs of t. Let's call it X of t. And the output voltage is Vc of t. Let's call it Yt. Now this is current. Current is, since it is a series circuit, same current will flow. And if we apply KVL, Vs of t is equal to Vr of t, the resistor voltage, plus Vc of t, the capacitor voltage. Now the current through the circuit is, as you know, when a current passing through the capacitor, I of t is C times the derivative of the voltage across the capacitor, C dVc by dt. Therefore, Vs of t is R times I of t plus Vc of t. Vs of t is equal to R times C dVc by dt. We substitute for I of t, C dVc by dt plus Vc of t. So Vc of t for us, we denote it as Y of t, and Vs of t, we denote it as X of t. So we have X of t is equal to Rc times dy by dt plus Yt. If you see this is a differential equation. Differential equation, what is the order of the differential equation? First order we have, because maximum what we have is the first derivative of the output y. And what is A0? A0, remember the A's are the coefficient for y of t, and the b's are the coefficient for x of t. So A0 means no derivative. The coefficient of y of t is 1, and A1 is the coefficient of dy by dt, which is Rc, and B0, the coefficient of x of t, is 1. If we change this to Laplace domain, so we have x of s. For the derivative of y of t, I will have s times y of s. So this will be s times Rc times y of s plus y of s. So what is common here? Y of s is common. Y of s is common. It will be s times Rc plus 1. Then h of s is y of s over x of s, which is equal to 1 over s Rc plus 1. If we rearrange this, take Rc common, and I will have s plus 1 over Rc. Then h of s is equal to 1 over Rc divided by s plus 1 over Rc. If we see this is a transfer function. See, transfer function, which is the form of this one, the form of like this, and B0 is 1 over Rc. B0 is 1 over Rc. So what are the poles of this? The pole is at s is equal to negative 1 over Rc, because at the pole h of s will be infinite. And what is the 0? The 0 is at s is equal to infinity. And most of the time we deal with causal LTI systems, linear time invariant systems. For t greater than 0, this means a right-sided signal, and the region of convergence includes real of s greater than negative 1 over Rc. Remember this one, 1 over s plus a. Remember 1 over s plus a. If the region of convergence is less than minus a, we have left-sided signal. If it is greater than minus a, we have right-sided signal. So using that, we have 1 over Rc constant here times A is 1 over RC here, so e to the power of negative 1 over RC times ut. This is h of t. So going from the Laplace domain to time domain. So you remember this is the impulse response of the simple RC low pass filter. And of course, when we go to frequency at s is equal to j omega, we have 1 over j omega RC plus 1. And we studied this also in chapter 3. Okay, so if we want, for example, to find the frequency response of the systems, we just evaluate the transfer function at s is equal to j omega will give us the frequency response of the system. So again, if we find the magnitude is given by this, and the phase is minus tan inverse of omega RC, and we have already this graph, if you remember. So 1 over RC is the cutoff frequency in radian per second, and it's like this, and it's simple low pass filter. And if we plot the region of convergence, remember the x-axis is the real axis, which is the sigma axis, and the y-axis is the j omega axis. So the pole is at s is equal to negative 1 over RC. So we have the broken line here because the pole is not included in the region of convergence. So the ROC will be real of s greater than negative 1 over RC, which is this one. Is this system stable? Yes, it's stable because the region of convergence includes the j omega axis. The j omega axis is, what is the j omega axis? The j omega axis is sigma is equal to 0, real of s, which is equal to sigma is equal to 0, which is this axis. Okay, block diagram representation of systems. Okay, we represent systems mathematically. That means we give a mathematical expression for systems. We can represent a system or characterize a system graphically, for example, by giving the impulse response as a function of time, or we can represent systems using block diagram. In this section, we will see how we represent systems in block diagram. For example, if you see this kind of representation, is called feedback representation. Okay, feedback representation. So if I see a better picture here, what is the feedback representation? I have the system input x of t here, and this one pass through this system h1t, and the output I have y of t. This is the output yt, and the output yt goes back to the second system h2t, and the output of h2t is z of t, and we have here minus, and we have the error function e of t is x of t minus zt. This kind of block diagram representation is called feedback system. It is used in control theory. It is used, for example, to control a system. For example, if we want to control the temperature in a certain room, for example, if we want the temperature of the room to fix it at 20 degrees centigrade, okay, we need to design a control system to keep at 20 degrees centigrade. If we want to, for example, to keep the speed of a vehicle, an autonomous vehicle, at a certain speed, for example, if we want to fix at 100 km per hour, so the input is 100 km per hour, that means the reference speed. So we need to design a system which will keep this reference speed. So which will keep this reference speed. For example, if we want an aircraft to fly at a certain speed, then also we need to design a system which makes the aircraft to fly at a certain speed, constant speed. Or if we want the aircraft to fly at a certain altitude above the surface of the earth, then we need to design a system to keep that altitude. So this is very common in control systems and very famous and very important in control systems, feedback system design. So this is called feedback systems design. This signal is called the error signal, E of t. And this one is an adder. So the adder has x of t input and z of t here, the output from the second system. And I have E of t, the error. The error is x of t minus z of t. So the error function will be an input to h1t, the main system, we call it here actually, the main system or the plant, we call it in control theory. So the output of the main system will have y of t. So if this is the main system, we need a secondary system. In the feedback loop, we need a second system to assist the main system so that the output will follow the input, okay, the reference input. Okay, usually when we have only the main system, we will not get the desired output. So that's why we need to have a second system, and we need to design feedback system like this so that we can have a good control system to control a certain reference input. For example, a reference speed or velocity, or a reference temperature, a reference pressure, a reference altitude, and so on. Okay, let's go back to the class notes again. Now, let's try to find the overall transfer function. So the overall transfer function in terms of H1 and H2. Now, what is y of t? Y of t is x of t convolved with h of t, yes? So y of t is x of t convolved with h of t, and when we change to Laplace, y of s is equal to x of s times h of s, then h of s is y of s over x of s. And what is the error? The error, E of t, is x of t minus z of t, okay, from this block, E of t, x of t minus z of t. And what is y of t in terms of the error signal? Y of t, E of t convolved with h1t. H1t is system 1, right? So the output of system 1 is y of t. So, but what's E of t? X of t minus z of t. Convolve everything by h1t. Therefore, this is x of t. What is z of t? Z of t means the output of the second system. The input of the second system is yt, and the output is zt. Zt is yt convolved with h2t. So yt convolved with h2t, and everything convolved with h1t. Now y of t is equal to x of t convolved with h1t minus yt convolved h1t convolved with h2t. Therefore, if we take this to the other side, y of t plus y of t convolve h1t convolve h2t is equal to x of t convolve with h1t. If we change to Laplace domain, this will become y of s. This one, the convolution, will become multiplication. So it will become y of s times h1s times h2s is equal to x of s times h1s. So what's common here? Y of s. Y of s into 1 plus h1s times h2s is equal to x of s times h1s. Therefore, y of s over x of s is h1s over 1 plus h1s times h2s, which is h of s. H of s is the overall transfer function. So that means if we say this is a block of the feedback system, if we represent the overall system by h of t, then h of s is the transfer function of the overall system, which is y of s over x of s. So in terms of h1s and h2s, this is the expression or the result for h of s. Okay, let's see some examples of block diagram representations. of some transfer functions. For example, find the block diagram representation of h of s is equal to 2s squared plus 4s minus 6 over s squared plus 3s plus 2. We can break this into two systems. Let's say the first one is 1 over s squared plus 3s plus 2, and the second one 2s squared plus 4s minus 6. Basically, the denominator, 1 over the denominator, is h1s, and the numerator is h2s. This is equal to ys over x of s. So h1s is 1 over s squared plus 3s plus 2. Let's call the output of h1s is ws. So w of s over x of s is equal to 1 over s squared plus 3s plus 2. And let's have h2s. h2s is ys over ws, which is a numerator 2s squared plus 4s minus 6. Now, from the first system, h1s, so x of s, the x of s is equal to, okay, if I do crisscrossing of this, x of s times 1 is equal to ws times s squared plus 3s plus 2, and then we have x of s squared ws plus 3s ws plus 2 ws. If I change it to time domain, this one, x of s is x of t, s squared ws is second derivative of wt, and sws is dw by dt plus 2wt. So what is this expression? This is time domain expression relating x of t to wt. Okay, now let's go to the second system. The second system is y of s over ws is equal to 2s squared plus 4s minus 6. Remember, h1s times h2s will give me y of s over x of s. If you multiply the two systems, h1s times h2s, so ws will cancel ws, and we will have y of s over x of s. So in the second system, we have 2s squared plus 4s minus 6 times ws is equal to ys. Again, multiply this, 2s squared ws plus 4s ws minus 6 ws is equal to ys. Then change it to time. 2 times the second derivative of w plus 4 times the first derivative of w minus 6 wt is equal to yt. We have two equations now. Using these two equations, we can draw the block diagram representation. The first is this one. Remember, this is the second derivative of wt by dt squared, x of t minus 3 dw by dt minus 2wt, and the second equation is relating wt to yt, 2 times second derivative of wt plus 4 first derivative of wt minus 6 wt is equal to yt. Let's see the block diagram. Now here we start with the input x of t, and here we have an output second derivative of w. But what's the second derivative of w? Second derivative of w is x of t minus 3 times the first derivative of w minus 2 times wt. So we have here another. But how do we get 3 times dw by dt? Okay, we have this, the second derivative of w, we will pass it through 1 over s. 1 over s means integrator. So if I do the integration of second derivative, I will have first derivative. And if I do the derivative of the integration of the first derivative, I will get wt. Okay, so that's how we get wt and first derivative. So after passing this through 1 over s, I will have first derivative, and I multiply it by a constant minus 3. Then I have here at this point minus 3 dw by dt. And here I have wt, and I multiply it by minus 2, and I will have minus 2 times wt. And I have here another which adds the 2, okay? and I have minus 3 dw by dt minus 2wt. So this is the output. The output of the first order is second derivative of wt, which is x of t minus 3 times first derivative minus 2wt, which is the first equation. The first equation is this equation. Now let's go to the second. The second one is yt. Yt is 2 times second derivative of w plus 4 times first derivative and minus 6 times wt. Easy. So we take from the second derivative and pass it through 2. Okay, so we have 2 times second derivative, and here 4 times first derivative and minus 6 times wt, and all of this adder, so it will add this, we'll get yt. This block diagram is called direct form block diagram. Okay, let's have more examples here. Let's say I have a system h of s 10 over s plus 5, where real of s is greater than minus 5. Draw the block diagram representation of the system. Find the differential equation relating the input xt and y of t. Remember, if I say real of s greater than minus 5, it is the right side of signal, and it is a causal system. So let's say h of s is y of s over x of s, 10 over s plus 5, and now crisscross this. S plus 5 times y of s is equal to 10 times x of s. So y of s times s plus 5 times y of s is equal to 10 times x of s. Then change it to time. S times y of s is derivative of y. 5 times y of s is 5 times y of t is equal to 10 times x of t. So if we rearrange this, because we need yt, yt is equal to 1 over 5 in bracket 10 times xt minus d by dt of y of t. So this is a block diagram representation. What we need here, first 10 times xt. So xt will pass through a constant multiplier. So that this is constant multiplier. So 10 times xt. It's like an amplifier, that means. So 10 times xt. And I have here another. Okay, 10 times xt minus d by dt of y of t. So I have y of t here, and it's feedback now. So how we get the derivative of y of t from y of t? I pass it through s. S, this is means s, okay? So I pass it through s, and I will get dy by dt. So this one is adder. So what is the output of this adder? 10 times x of t minus dy by dt. Okay, so we reached to this part now. So what is left? To get y of t, we multiply everything by 1 over 5. So this is a constant 1 over 5. So multiply by 1 over 5, we will get y of t. So this is the block diagram representation of this system. Is this system stable? Yes, of course. Why? Because the ROC includes the j omega axis. ROC is this one. It includes j omega axis, which is the real of s, which is equal to sigma, which is equal to 0. Okay, let's have another example. Represent the following system as a cascade connection of two systems. So we have the transfer function. From the transfer function, we will find the block diagram representation. Represent is as in the form of cascade systems. So I break this into two systems again. First system is H1s, second system H2s. So H of s, y of s over x of s, 1 over s plus 2s plus 3 is equal to H1s times H2s. What is H1s? Let's say H1s is 1 over s plus 2. And H1s, the output of the first system is W. So let's call it Ws over x of s. H2s is 1 over s plus 3, which is y of s over ws. The input to the second system is w of t, and the output is yt. So y of s over ws is equal to h2s. If we multiply h1s times h2s, ws will cancel ws, and we get y of s over x of s, the overall system. So let's have the first system, h1 is ws over x of s, 1 over s plus 2. Crisscross this, ws times s plus 2, x of s times ws plus 2 ws x of s. Change it to time domain. The derivative of wt plus 2 times wt is equal to x of t. 2 times wt is equal to x of t minus dw by dt, which means wt is equal to 1 over 2, because I need the output wt, 1 over 2 times in bracket x of t minus d by dt wt. So this is a feedback system again. Okay, and let's go to the second system, h2s y of s over ws, 1 over s plus 3 crisscross, and we have y of s times s plus 3 ws. S times y of s plus 3 y of s is equal to ws, dy by dt plus 3yt wt. Then rearrange this, y of t 1 over 3 wt minus dy by dt. So another feedback system, two feedback systems cascaded to each other. The output of the first feedback system is wt. The output of the second feedback system is y of t. So if we draw this, remember this is the first feedback, wt 1 over 2 x of t minus d by dt wt. So let's go to the next one, this one. This is the feedback system, h1t. So let's see this adder. The adder has x of t minus dw by dt. How we get dw by dt? The output of the first system is wt. It will pass through s. This is s. So in Laplace domain, at this point I will have s times ws. When I change it to time, it will be dw by dt. So this is another x of t minus dw by dt is the output. Multiplied by the constant half, I will get the output wt from the first equation. From the second equation, let's go to the second equation, 1 over 3 wt, but the input is wt, minus d by dt of y of t times 1 over 3 is equal to yt. So again, the input is wt. The feedback signal is dy by dt. How I get it? From y of t, the output, y of t, and pass it through s. In Laplace, it is s times y of s, and in time, dy by dt. So at this point, I will have wt minus dy by dt multiplied by 1 over 3, I will get y of t. So this is cascade connection. The first system, y of t, x of t convolved with h1t convolved with h2t, y of s, x of s times h1s times h2s, which is equal to x of s times h of s. What is h of s? The overall system. h1s times h2s, or in time domain, h of t is equal to h1t convolved with h2t. This is called cascade implementation, block diagram cascade implementation, or series connection of first system and the second system. That means the two systems are connected in series. The same system, I can implement it using parallel connection. If I want to implement it as a parallel, two parallel systems, I need to do partial fraction expansion. So h of s, 1 over s plus 2, or times s plus 3 is equal to a over s plus 2 plus b over s plus 3. So I will have y1s over x of s, which is a over s plus 2. We need to find a and b first from the partial fraction expansion. So y1s over x of s, a over s plus 2, and y2s over x of s, a over b over s plus 3. So I have the two systems having the same input, x of t. Okay, so h1 is a over s plus 2, H2S P over S plus 3, and I have output Y1T and Y2T. The addition of the two will give me Y of T. Y of T is Y1T plus Y2T, and you can try to do by yourself. This can be as a practice exercise. So that's it about transfer function and block diagram and differential equations. For example, here also I have another example. This is an RLC circuit. In this case, the input signal is a voltage, for example, and I have a resistor, I have inductor, and I have capacitor. We are interested to find the output Y of t, which is the voltage across the capacitor. And if we try to write the differential equation relating x of t and y of t, I have r times c dy by dt plus lc second derivative of y of t by dt plus y of t is equal to xt. Remember, y of t is the capacitor voltage and x of t is input voltage. Then y of s over x of s, which is the capacitor voltage over the input voltage in Laplace domain, will give me h of s. And if we rearrange it, we will have 1 over LC s squared plus r over ls plus 1 over LC. So we can change this to time domain. If we have r and l and c, the parameters of r, l, and c, we can change it to time domain, and we can find the function, and we can plot it and so on. Okay, that's all about LTI systems and differential equation and how to solve them using Laplace transform. Please redo the examples in this chapter and try to make practice on the class exercises posted in Blackboard to have more understanding. And thank you for listening to this lecture.